Hello everyone, in this video we are going to talk about Quicksort. So in the previous video of sorting algorithms, we have talked about the merge sort, the very first sorting algorithms that works in n log n time complexity. This is the best time complexity that we can get for a general sorting algorithm. This is all good about the merge sort, but the issue was that merge sort is not in place. The part of the sorting which actually merges two sub-arrays needs to create another array to be able to sort two parts, right? Remember, the idea of the merge sort was you have an array, the original array that you wanted to actually sort, and you find the middle index, you divide it at the middle to two arrays, okay, and recursively just sort the each part, the first half and the second half, recursively just sort them, and then you have to merge these two. So it's just like you get them sorted, and then to get the original array sorted, you have to merge these two arrays to a larger array. And this part, the last part, which is called the merge part, cannot be done in place. You have to actually create a new array and copy the values from these two sub-arrays inside this larger array. So this is exactly the issue with the merge sort. Everything else about the merge sort is good, except that this is not in place. And we want to see that, is it possible to kind of get rid of that merge step so that we don't need to merge two sub-arrays? If yes, we can make the merge sort in place. So the whole issue here about the quicksort is that we wanted to modify that idea of the merge sort so that we get rid of the merging step. Okay, so what is the how the quicksort is going to actually fix this issue, the issue of merging? The point is that in the merge sort, you divide the array to two parts based on the location, right? You just find the middle index, okay? You find the middle index, and just based on that, you divide it to two parts. And because some items here are going to be smaller than some items here are going to be at the end when you are actually just merging, some items here are going to be larger and some items here are going to be smaller and go to the first part, okay? What if instead of dividing the array based on always just the middle point without thinking about the items that you have, what if I find some point in the array and say that, okay, if I find some point in the array, not necessarily the middle point, somewhere, for example, here, and say that I am going to kind of partition, rotate the items so that everything in this part are going to be smaller than everything in this part, and then divide the array at this point. So what this property actually give me? This property gives me this good situation that if everything here are going to be less than everything here, at the end when I am actually dividing the array to these two parts, if I get this part sorted and if I get this part sorted, I don't need to merge them because I already know that everything here, they are sorted and they are greater than everything here. So I'm not going to actually get rid of the merging step. Okay, actually these three pictures summarize the whole idea of the quicksort. That you choose an item. Okay, so I don't care which item, just randomly I choose an item from all the items that I have. So for example, these are the items that I have, and these are the items. I randomly choose an item, pick an item, we call it pivot actually, and then I will rotate, I will just partition the items inside the array based on the value of x, so that it's just like you find the position, the correct position to put x among all the items. So for example, something like this, that x is at its position and everything to the left of x are smaller than x, and everything to the right of x are greater than x. Okay, so this is critical, and this is very actually important for me, this step, that how to find the correct position of x, put it at its correct position. So x is at its correct position, everything smaller than x are at the left of x, and everything greater than x are at the right of x. Okay, so if then I can actually just recursively apply that sorting algorithm over the first part and over the second part, and at the end you will see that I don't need to merge them because already everything here is smaller than everything here, and x is at its correct position. So I just got rid of the merging step. This is exactly what I wanted to do to fix the issue with the merge sort which is not in place. So if I wanted to actually show you the code for quicksort, this is very similar to the merge sort. I mean, the main code, that recursive function, almost exactly the same as the merge sort. The difference is that first I'm calling it actually a quicksort. The second thing is that I don't have the merge part. You can see that I have two function call, two recursive function calls for sorting the left side, for sorting the right side, and I don't have any merging. I don't have that merge method that we had for the merge sort, right? So I just got rid of that, but I have to add one more method. This method partition is basically doing this step, that finds the just randomly choose an item like x, put it at its correct position, and also partition, rotate the items so that everything to the left of x is smaller than x, and everything to the right of x is greater than x. Okay, so these steps, this step 2, will be done using this method partition. Okay, so the rest of it is just the details of the implementation. So the method, remember we have discussed that we don't want to create new arrays and passing the and returning the actually arrays in the recursive function specifically. So that's why we define two indexes that shows that which part of the array we are working. So all these details are exactly similar to what we did for the merge sort. This low and high is exactly just like whatever we defined for the merge sort and in the recursive method of the merge sort. And the base case here, I'm actually showing it the base case very clearly, that if the low is smaller than high, if the low is greater than the high, basically means that this indexes low and high tells you that which part of the array you are working on. So if you have a larger array, if you recursively are working on it, that for example low is here and high is here, low, high, you are just, it means that you are working on this part of the array recursively. Okay, and whenever the value of low became greater than high or equal to high, it means that the size is less than or equal to 1, which is the base case, and you don't do anything. If the array is empty or if it is of size 1, it is already sorted. You don't need to do anything. Otherwise, you partition the array. This pivot index is important for me. Why? Because as you can see, we don't necessarily divide the array to at the middle point. Basically, we divide the array based on the pivot index. What is the pivot index? The pivot index is going to be the position of x. Pivot is the value that you choose from the items in the array, and pivot index is going to be the position of actually x in the array. So everything before the pivot index will be passed to the first function call, the first recursive call, and everything after the pivot index will be passed to the second recursive call. So here's the thing, the pivot index is important for me. This is actually tells me that from low to pivot index -1 will be the first half. From pivot index +1 to high will be the second half. So it's actually working like this. So this is going to be, for example, the pivot index. So because the item x at the index pivot is already at its position, I don't need to actually sort that. So this part is going to be the first half from low to pivot index -1, and from pivot index +1 to high. This is going to be passed to the second function call. Okay, so let me actually just show it to you over a few examples. Maybe that actually helps. Assume that I have an array like this one. I'm going to sort it, so you randomly choose an item. Just assume that I got 44. Then we partition the items. You can see that I chose 44, but in the original array there are some items on the right of 44 which are smaller, and there are some items on the left of 44 which are greater. So I need to partition these items, all the items around 44, and put the 44 in its correct position. So it's just like I am making this change into the array. Now everything to the left of 44 are smaller than 44, and everything to the right of 44 are greater than 44, right? So then quicksort will be called recursively over this part, and it will be called over this part. So it's just like you are going to call the quicksort over this part. Let's just actually put some indexes over that as well. So it's just like then you call the quicksort over this part. You see that the pivot index is 6. So it's just like you call the quicksort over 0 over the original array index 0 and until pivot index -1, which is 5. Okay, then over this half again find, randomly choose an item as a pivot. Just assume that we choose 10. Then 10 will be inserted at its correct position. So you partition the items. Probably I have sorted the items, not instead of actually partitioning them. So let's just actually make some changes here. Something like this, 43, 12, 38, something like this. You partition it in this way. So 10 is at its correct position. Everything to the left of it is smaller and everything to the right of it is greater. Something like this, not exactly the same, but anyway. Then you call the quicksort over the first half. Basically, this is going to reach to the base case. It's just like, because this is index 0, and it will be like you call the quicksort over the original array, the low and the high, both of them will be 0, which actually means that the size of the array is 1. So this reaches to the base case and it doesn't do anything basically. So this part will be sorted. Then you call the quicksort over this part, which is going to be the quicksort from index 2 to index 2 to 5. Okay, then you choose a pivot index again. Randomly choose an item, for example 26, then partition the items around 26. So 26 will be at its position. You call the quicksort over this part and you call the quicksort over this part. You see that when you are actually calling the quicksort over this part, the low and high, both of them will be equal to the index 2, which basically means that the size of the array is just 1. The array is already sorted. So this is the base case. You don't do anything. Then you call the quicksort over this part. Then again you choose a pivot value. Let's just assume that the pivot value is 43. You partition the items around 43. So 43 will be at its position. Everything to the left of it is smaller. Everything to the right of it is greater. There is nothing to the right of it, so that's it. You call the quicksort over the first half. You call the quicksort over the second half, which is here, which is empty again, the base case. And now you can see that after we are done with calling recursively over the first half and everything is in place. Everything is smaller than 44. So later on, when we call the quicksort over the second half and get this part sorted, we don't need to merge them. We just got rid of the merging step. So now the question is how I am going to implement the partitioning step. This is very important, right? Find the correct position of the pivot, put everything smaller to the left of it, everything greater to the right of it. So if I'm going to show you the full implementation will be a quicksort, the recursive function, and also the method to implement partition. The method partition, right? Which actually takes 2 arguments, low and high, tells me that, okay, find a pivot value in this between low and high, put it in its correct position, and return the index as well. Also actually put everything to the smaller than that to the left of it, greater than that to the right of it. I wanted to see that how I can implement the method partition. I'm going to give you the algorithm, but I am not going to write down the full implementation. This is something that you will do in the lab exercise for this week. Okay, how we are going to implement the method partition. The method partition has 2 basic jobs to do. It needs to choose a pivot value, put it its correct position, and put everything smaller than that to the left of it, everything greater than that to the right of it. So we can just simplify choosing the pivot value. As for now, just assume that we randomly choose one item from the array. It doesn't actually matter then which item, just randomly choose one of them. Then what we can do, the very first actually trivial algorithm that comes to mind is that, okay, I can copy the item, swap it, for example, randomly choose one item and swap it and put it as the last item in the array. But wherever, just for example, the last item in that part of the array that I am sorting. And then go over every item. If it is greater than the pivot, just one thing. I can create some additional array, okay? Create some additional array. This is, the array actually is here, but just to show you that what would happen. You create some additional array of the same size. This is going to be of size 8. Okay, of the same size, and check each item from the first item. If it is greater, you copy it at the end of the array, for example 85. You define one index here and one index here. Then the next item, if it is a smaller, you copy it here, and then you update the index as well. The next item is greater than 50, you put it here and then update the index. The next item is smaller, you put it here and update the index. The next item is smaller, you put it here, 17, and update the index. The next item is smaller, you put it here and update the index. The next item is greater, you put it here and then update the index. When you stop, whenever these two indexes actually reach to each other, both of them are referring to the same position, where basically that position is going to be exactly the position that you should put your pivot item. Okay, so the algorithm is very nice. It works. The time complexity is linear, right? You just actually scan all the items from left to right and put all the items here, and you can see that everything here is smaller than 50 and everything here are greater than 50. Everything is good except one thing. This algorithm is not in place as well, right? I am using some additional array. So what did I do? I didn't really actually solve that issue of the merge sort. I just make it more complicated, basically. So no, this algorithm is not going to be acceptable and I can't use this one. I wanted to make sure that the quicksort can be done in place. I don't want to use additional array. So let me show you an algorithm which is basically there are more than this. I'm sure that if you search online you will find some other algorithms different than this one, but I found this one more I don't know, just I found it more fun, more interesting. But anyway, this is not the unique algorithm. There are some other algorithm for partitioning as well. So what is the idea here? We choose a pivot. Just assume that we randomly choose one item in that part of the array that we are working on, and we choose it as the pivot. And again, what I'm going to do, I'm going to swap it with the last index of that part of the array that I'm partitioning. It's just I'm putting it at the end. It's just like I'm putting it aside. Okay, so I choose 44. I chose, for example, the middle index, randomly just chose the middle index. I don't know what is the value of the middle index. Maybe it is the smallest item, maybe it is the largest item. Just assume that I choose, for example, the middle index, and then swap it with the last item. Just put it aside at the last item. So 44 is my pivot, but I swap it and put it here. Then what I'm going to actually do is that I'm going to scan all the items in the array and just keep swapping them around and find the correct position of the pivot index, then put the pivot index in that position. So let me actually, instead of giving you the algorithm in terms of the pseudocode, I'm going to run it over this example, just explain it over this example, and I believe this is going to make it much easier to understand. So I will define some variable as the pivot index, and I'm going to initialize it as the beginning of the array. Here in this example that I'm working on the full array. So I'm going to initialize it as a 0. Okay, then I am going to start scanning all the items from the first item. That again, so here I'm going to work on the full array. So I'm going to start at index 0. What I'm going to do here is that I would assume that everything to the left of pivot index is smaller than the pivot. Okay, so everything to the left of the pivot index, because pivot index is 0, everything to the left of it, there is nothing to the left of it, right? So that's correct. Everything to the left of it is smaller than the value 44. So what I'm going to do is that I'm checking each item at the value, I'm scanning every item at the index I, starting from index 0. If it is smaller than the pivot index, I have to basically move it before the pivot index, right? But if it is greater than the pivot index, it's just like it is after the pivot index, and I don't need to do anything with that. So I am checking one condition. If the item at array index I is greater than the pivot, I don't need to do anything. But if it is smaller, for example, for the actually case of the 80, I didn't do anything. Then I'm going to actually check the next item. The next item is 38. What if I am actually comparing the item at index, for example, 1 with the pivot, which is 44? What would happen? This is going to be smaller than 44, right? This is 38. The value of I, let's just assume that the value of I is 1, okay? And I'm checking this item. Because it is smaller, I have to move it before the pivot index. But there is no other space. I don't have some additional space. What I'm going to do is that I am going to swap the value at index I and the value at the pivot index, okay? And then it's just like I'm putting that value behind the pivot index. And then I will increase the pivot index to just make some space. So what I'm going to do is that I will swap the item at index I and the item at pivot index. And then after that, I will increase the pivot index to just make sure that, again, everything to the left of pivot index is smaller than the value of pivot. And everything after than that is greater. But until where? Until the value of I. Because I haven't actually checked the rest of the array. But one thing that I will be sure is that everything to the left of the pivot index is smaller. Then you will actually just continue. You continue and check the next item. Scan the next item. The value of array at index 2 is greater than the pivot, so I don't need to do anything. The value at index 3 is greater than pivot value, so I don't do anything. The next item, the value at index 4 is greater than the pivot value, I don't need to do anything. So be careful, just think about each step. Always everything to the left of the pivot is smaller than the pivot, and everything to the right of the everything to the left of the pivot index is important for me. Everything to the left of the pivot index is smaller, and everything after the pivot index is greater. Until where? Until here. So this is a state invariant, which after each at the end of each iteration, this is correct. Everything to the left of the pivot is smaller than 44. Everything after the pivot index is greater than 44, right? So everything here is smaller and everything here is greater. Now let's actually just continue and check one more step. At index 5, I found something which the value of that is smaller than the pivot. Remember what was the actually the pattern? If we find anything smaller than or equal to the pivot value, what we will do, we will actually swap the items at the index I and the item at the pivot index. So I'm going to swap these two items, and then it's just like you get the item, put it before the pivot index, and then because you don't have enough space, you just move the pivot index to make some space. So after you swap them, you update the pivot index. By updating, I mean you just increase it, so you make some space. Now again, everything to the left of it is less than 44, and everything after than that are greater than 44. Okay, until here. I mean, among all the items that you have scanned. So you go forward, the next item, it is greater than pivot index, so don't do anything. The next item, it is smaller than pivot index, it is smaller than the pivot. So what we do, we swap the item at index I and the item at the pivot index. We swap them, and then you update the pivot index. So again, everything to the left of the pivot index is smaller than the pivot, and everything to the right of the pivot index are greater than the pivot. The next item again is smaller, so you swap the array index I and the array pivot index, and then update the pivot index. And the next item, 87, it is greater, you don't do anything. The next item is 96, it is greater, you don't do anything. The next item is 12, it is smaller, so we swap I and pivot index and update the pivot index. Okay, the next item is again smaller, so you swap the value at index I and pivot index, and then update the pivot index. So you see that everything before the pivot index is smaller, and everything after that are greater. The next item is 81, it is greater, you stop. You actually don't do anything. Okay, I will stop. Why? Because I have scanned all the items until the last item. What is the last item? The last item is basically the value of the pivot, right? Remember at the beginning, I put it at the last index. It's just like I put it aside. Now you can see that everything before this index is smaller, and everything after this index is greater than the pivot. What I can do here is that now I have to take this item and put it at its correct position, which is basically here. But I should be careful, because now currently at the position of the pivot index there is an item from the original array. I shouldn't lose this one. What I can do is that I can swap this item and this item. So basically I need to swap the index, the value at this index, the last one, and the pivot index, just to make sure that I'm not losing 79. And it is safe because whatever was here before was greater than the pivot value. So you can safely swap it, and now 79 is on the right side. So 44 is at its correct position. Everything smaller than that is at the left of it. Everything greater than that is at the right of it. Okay, so we are done. The the partition algorithm just need to return whatever is the pivot index. What is the time complexity? The time complexity is linear, right? Because basically what I did was just checking every item once, and for each one I just check an if statement, right? If it is greater, don't do anything. If it is smaller than or equal, just do a swap and increase the value of the pivot index. So this is linear. The time complexity of this algorithm is linear, and it can be done. It is in place. I didn't use some additional array. Right? Just one thing about the about this algorithm, basically just for your lab, when you are actually implementing this algorithm, you should be careful when you are calling. For example, just assume that you call the quicksort over the original array. Okay, so the original array is from index 0 to index 14, for example, and you call the partition method. The partition method was exactly this step that I showed you. Okay, 44 was the pivot, and it shows 6 as the pivot index. It returns 6, and then what would happen? It will call the quicksort from index low, which is 0, to pivot index -1, and then it will call the quicksort on the right side of it, right, from index 7 to index 14. So be careful whenever you are calling the method partition. For example, if you call the method partition over this part, so you start from low to high. What is high? High is, so what I explained there was over the original array. You should be careful that you should stick to these indexes from low to high, and so when you are implementing the method, the value of I should be initialized at low, and it should go up. You should increase it until you reach to the value of high -1, which is going to be this index, right? I just wanted to actually just remind you that you are working not on the full array always. You are working on a part of the array each time, from low to high. Okay, so now let's actually think about the time complexity and see that how the partitioning method is going to affect the time complexity at the end. I'm going to show you two different cases that the partitioning algorithms, what would happen if the partitioning algorithm chooses some item as the pivot, as the item is, for example, close to the middle point, or if it chooses some very small item or very large item. So these two cases are going to be completely different. So here the discussion is about the time complexity. I wanted to see that what is the time complexity of the quicksort. the time complexity of the quicksort, the discussion is going to be very similar to what we did for the merge sort. This is a recursive function, okay? So if I wanted to find the time complexity, I need to find a recursive relation for the time. So it's just like you are going to find a T of n method. I don't know what is T of n, but I can actually just define it recursively. What is T of n? T of n is the time that will take to execute the quicksort over an array of, what is the size of the array? The size of the array is going to be, let's just assume that this is n, where n is equal to high minus low, right? Basically, this tells me that what is the size of the array. So based on that, n is the size. I don't actually care that which part of the array you are actually sorting. Just the size is important for me. I wanted to know that how much time it would take to execute quicksort over an array of size n. If you think about what I have here, I would have a partition method. The time complexity of partition, I know that this is going to be theta of n, or you can actually just, instead of theta of n, you can write it as cn. Doesn't really matter, right? Where n is the exactly again high minus low, the size of the array, how many items you have in the array. And I also have two recursive function calls. These two recursive function calls are not quite clear that which part of the array they are sorting. Why? Because everything depends on the pivot index. So you can actually here see that if this is the original array that I have, and then if the pivot value is at the middle point, this will be similar to the merge sort, right? Because it creates two parts, the first half and the second half, and this part is going to be of size, for example, n divided by 2, and this size is going to be n divided by 2 as well, right? If the pivot value is at the middle index, almost n divided by 2, so basically it's going to be n divided by 2 minus 1, n divided by 2 minus 1, but it doesn't really matter, so I'm going to just keep it as n divided by 2 to make it simpler to discuss, right? So if the pivot value is returning something at the middle index, so these two halves are going to be of these two quicksort calls, these two recursive calls are going to call over equal sizes, right? The first half and the second half. So these ones are going to be T of n divided by 2, and this one is also T of n divided by 2. So the final formula for me in this case is going to be T of n will be equal to 2 T of n divided by 2 plus the cost of partitioning, which is going to be Cn, right? If the pivot index is here, if the pivot value is the median of all the items. And what we know about this formula is that this is exactly the formula for the merge sort. So I already know that if I solve this algorithm, this is going to give me theta of n log n. Okay, so this is one case. The other case is that what would happen if the pivot item that you choose, because we randomly choose a pivot value, right? We don't know if this is going to be the median value. It can be any of the items. What if the item that you choose is going to be the largest item, for example? If it is the largest item, this is going to be the pivot index, right? What this is going to actually tell me, let's just actually use a different color here. This is the second case. Pivot index. Okay, so in this case, the cost of T of n is not going to, the cost of partitioning is not going to be changed. Still, it doesn't matter what is the value of the pivot, you know that the cost of partitioning is going to be Cn. But it is dramatically change what would happen over these function calls. So if the item the pivot index is the largest item, what would happen? You have to call the quicksort over this part of the array and over this part of the array, which basically you can here see that the cost here is 0, okay, because the array is empty, basically, right? There's nothing after the largest item. But what is the size here? The size here is n minus 1. So what would happen? The time complexity, one of these recursive calls is going to be, the cost of it is going to be T of n minus 1, because the size of the problem is n minus 1. You just remove the largest item, right? And the rest of it is n minus 1. And this one is going to be T of 0, which basically you can say that this is negligible, this is 0. So what is going to be the recursive relationship in this case? T of n is going to be equal to T of n minus 1 plus Cn. You can see that I have actually remove this T of 0 because the cost is 0. So you can see that this recursive relationship is completely different than the other one. I have to solve this one and see that what I get as the result of this one. Before I move to solving this, let me actually show you the other case, that what would happen if the pivot item that I choose is the smallest item. Okay, so this is the pivot index. If you choose the smallest item, again, what would happen? You call the quicksort over this part, which is basically 0. Anything is smaller than the smallest item, there's nothing, right? So one function call will be 0. The other function call will be over this part of the array, which is of size n minus 1. Okay, so in this case, this one is going to be T of 0, which is negligible. You can just consider it as 0. This part is going to be T of n minus 1. So I'm just trying to tell you that if you choose the largest item or if you choose the smallest item, the time complexity will be the same. In both cases, the recursive relation is this one. T of n will be T of n minus 1 plus Cn. So now let's just solve this recursive relationship and see that what we are going to get for the time complexity of this recursive relationship. We have solved this one already. We know that this is going to be n log n based on the merge sort. I'm going to show you that what would happen to this case. Okay, so what we are going to do is, again, I'm going to exactly follow the same approach that I did to solve that T of n equal to 2 T of n divided by 2 plus Cn. We actually solved this over the merge sort by substitution, right? You remember I keep replacing T of n divided by 2 again by the same formula, so it actually make it something like this: T of n divided by 2 power 2 plus 2cn, and then we actually keep substituting until we just completely remove this recursive part, right? So I'm going to do exactly the same for this formula. So I'm going to replace this part with the recursive relation for that. So I know that t of n minus 1 will be, what I'm going to do is that I'm going to use the same relationship, just take n and put n minus 1 inside instead of that. So this one is going to be n minus 1, and basically let's just write this one as c of n because it's much easier to work on. And instead of n, I'm going to write n minus 1 as well. So t of n minus 1 will be t of n minus 2 plus c multiplied by n minus 2, right? Let me just erase these parts. Okay, I'm going to get the whole relationship here and just replace it instead of this one. Let's just use a different color. Okay, by replacing that, I will get something like this. Okay, I make the value inside the parentheses smaller. Basically, I just wanted to make it smaller and smaller until I reach to this case. Okay, or t of 0 equal to 0, basically. So these are the base case. You can replace them and just totally get rid of that the recursive part of the relationship, the relation. Okay, so again, I am going to take this one, replace it with, what is t of n minus 2? T of n minus 2, you can replace it with t of n minus 3 plus c multiplied by n minus, sorry, this one, it was n minus 1, and this one is going to be n minus 2. So I will take this part and replace it. And so this part will be t of n minus 3 plus c multiplied by n minus 2 plus c multiplied by n minus 1 plus c multiplied by n. So now you can actually see the pattern. This part will get smaller and smaller, and each time one term will be added to this one. So if I continue make it smaller and smaller, it's just like I reach to this situation that I will add all of these terms until I reach to t of n 1. That t of 1, you can replace it with 1, for example, or you can actually, just to make it simpler for the formula, you can replace it with c. Basically, there is no difference, right? This is constant, either 1 or c. Doesn't really matter. I'm going to write it as c to make it, much nicer when I'm writing the formula at the end. So what I have here is just the multiplication of c to the summation of I, where I is equal to 1 to n, right? This is exactly just the summation of 1 to I. We already know what is the result of this summation. This is going to be n to n plus 1 divided by 2. You just multiply some c factor to that as well. So in total, the time complexity of this recursive relationship, this one at the beginning, the time complexity of this recursive relationship is going to be theta of n power 2. You see, there is difference between these two cases. This is not like the merge sort that always you find the middle index and you divide it to half size. That's why I'm telling you that everything here depends on the value of the pivot. If you choose a pivot value which is close to the middle point, you get to this formula. If you choose a pivot value which is very small or very large, you get this recursive relation. This one is going to give you theta of n log n, unlike this one, which is going to give you theta of n power 2. So there are two different cases, the best case and the worst case. The best case of the quicksort is going to be n log n, like the merge sort, if you choose a pivot value close to the median. And the worst case is when you are choosing a very small item or a very large item. This is going to give you theta of n power 2. I think actually the idea is very intuitive, because when you are finding something at the middle, it's just like you are making the problem, you are dividing the problem to two parts, and you are making it, it's just like you are making it of size half. Each time you make it of size half, compare it to this case that always you find something very small or very large. You will make a very small problem and a very large one. Okay, that's why the time complexity of this recursive relation, this one, is bigger than the time complexity of the other recursive relation, which was 2 of t of n divided by 2 plus cn. Although this is solving two sub-problems, but those two sub-problems are much smaller than this one sub-problem that you are solving here, which is a very large sub-problem. And mathematically we can show that this one is going to be theta of n power 2, this one is going to be theta of n log n, which is clearly n log n is way better than n power 2. So now that we know the time complexity of the quicksort will depend on the value of the pivot, the question that came to mind is that how we can choose a good pivot. There are different actually heuristics and algorithms to modify quicksort and make sure that the pivot value that you choose is a good pivot value. I'm going to just introduce one of the simplest form of these algorithms. So this is a very simple heuristic, which is called the median of 3. What we do in this case is that instead of just randomly choose an item, or instead of just always pick, for example, the middle index, because you never know that what is the value at the middle index, right? Instead of always just randomly choose an item, you will look at the item at the beginning of the array, the item at the end of the array, and the item at the middle index. Compare all these three items and find the median among these three. This is going to give you just an approximation about what is the median of all the items. This is not going to be the median of all the items, of course, but still it gives you a good approximation, and it gives you a very good heuristic for finding a value for the pivot. Of course, if you can find the exact median value, that's going to be best, but finding the median of all the items in the array is going to be costly. So you can't just pick an item as the median. It is going to take some cost. That's why we just use some heuristic to find some value as the value of the pivot. So before actually finishing this lecture, I'm going to just summarize what we discussed about the quicksort, the time complexity of the quicksort. Unlike the merge sort, that there is no average case or the best case or the worst case, always n log n. In the case of the quicksort, the best case and the average case, if you find a good pivot, is going to be n log n. but the worst case run is going to be theta of n power 2. About the space complexity, in the method for the merge sort, because you cannot do the merge in place, the space complexity for the merge sort is going to be linear, but the space complexity for the quicksort will depend on the value of the pivot again. And the reason is that when you we are not explicitly taking some space. That's right. We are not doing anything like merge, or even in the partition method, you are not using additional array. But remember that we are going to have a recursive method, right? And that recursive method is going to take some space from the stack. For each recursive call, you have some function call that will be stored inside the stacks. Function calls. Okay, so depending on the way that the value of the pivot, either you need to have log of n number of function calls at each time, at the most inside the stack, or if you are actually finding a very small or a very large pivot value, the number of function calls that you keep inside the stack is going to be depending on n. So that's why the value of the pivot not only affects the time complexity, it also affects the space complexity for the quicksort. So this is that's it. This is all the topics that we all our discussion about the quicksort. If you choose a good value for the pivot, you can always make sure that this is the time complexity is n log n, and we say that this is almost in place. Usually it is called that almost in place because although we are not explicitly using some space, because of those function calls and the recursive the format of the quicksort and the space that you need to use to keep the function calls inside the stack, that's why some people don't call the quicksort exactly in place. It just it's the matter of how you define the term in place. Some people define it in this way, that if we are using some additional space in terms of n, this is not going to be in place anymore. But some people are just define it as if we are not using additional array of size, depending on the size of the input, we are calling it in place. So it just actually depends on the how you define the term in place. So that's it for this lecture.